Dear all, I am Dr. V. Malati, Associate Professor, Department of ECE, SR University, Varangal. In this video lecture, I am going to simulate body temperature measurement using thermistor. So, what we will measure, average measured body temperature is equal to 37 degrees Celsius for normal human being. Then body temperature measurement using thermistor, we will give a graph of time in second versus temperature in degrees Celsius. I have written code in Python and I am going to simulate in Google Colab platform. Now I am going to share the screen. See, the output average measured body temperature is 37 degrees Celsius, and we got the waveform of time in second versus temperature in degrees Celsius, and this graph is known as body temperature measurement using thermistor. And actually the two waveforms, dotted waveform and solid waveform, both are coincidence, both are in coincidence. So blue waveform is true temperature degree Celsius and the measured temperature is degree Celsius. It is in red color. So both are coincidence with one another. And now I am going to explain the code line by line. This experiment simulates temperature measurement using the NTC thermistor, that is negative temperature coefficient thermistor. It applies the heart equation and plots the measured body temperature. So what this code does, first one, it simulates thermistor resistance variation with temperature, and then it uses voltage divider circuit model. Then it converts measured voltage into resistance and then temperature. Now plotting the voltage versus time, resistance versus time, and then temperature versus time. Actually, what is negative temperature coefficient thermistor? If temperature increases or resistance increases, means that is positive temperature coefficient. If temperature increases, resistance decreases, means that is inversely proportional. Then it is negative temperature coefficient thermistor. And now what is the principle? And NDC thermistor decreases resistance as temperature increases. Using the beta equation, temperature is calculated. T equal to, normally the beta equation is T equal to 1 by T naught, that is initial temperature, plus 1 by B ln R by R naught. So R is resistance at any time and R naught is the initial temperature, that is R naught at T naught, R at T. Then typical output what we will get, normal body temperature, which is equal to 36.5 degrees Celsius to 37.5 degrees Celsius. Then small sinusoidal variation simulates physiological fluctuation. And then, so first one we take numpy, that is NP. It is used for mathematical calculations such as logarithm, sine, exponential and arrays. And then matplotlib dot pyplot plt. It is used to plot graphs such as a histogram and one graph of one parameter versus another parameter, and then box plot and so on. And then here thermistor thermistor parameters I mean specifications are given, that is R naught equal to 10,000, resistance at 25 degrees Celsius, it is 10 kilo ohm thermistor. T naught equal to 25 plus 273.15. So reference temperature in Kelvin. So Celsius to Kelvin conversion. B equal to 3950. It is beta constant. And then Vs is equal to 5. That is supply voltage equal to 5 volt. And then R underscore fixed is equal to 1000. So fixed resistor, that is voltage divider. There are known parameters of the thermistor circuit, that is R naught equal to 10,000, that is thermistor resistance at 25 degrees Celsius is 10 kilo ohm. Then T naught equal to 25 plus 273.15. It converts 25 degrees C to Kelvin of 298.15 Kelvin. And then temperature calculations must be done in Kelvin using Python. Then V equal to 3950. It is material constant of thermistor. So it may vary slightly depending on the material used for manufacturing the thermistor resistor. Then VCC supply voltage, it is normal common, and R fixed equal to 10K, that is fixed resistor used in the voltage divider circuit. Then simulated body temperature. So it is sampling frequency equal to 100. Then T equal to NP. NP dot linspace 0, 10, Fs into 10. Fs into 10. So sampling frequency equal to 100, that is 100 samples per second. Time array from 0 to 10 seconds. So duration equal to 10 seconds. So simulating body temperature. True temperature in Celsius is equal to 37 plus 0.2 NP sine 2 NP 0.05, that is that is frequency, frequency into time. So here normal body temperature is 37 degree and degree C, and small sinusoidal variation of plus or minus 0.2, and then simulates natural physiological fluctuation. Then it converts to Kelvin. So true underscore temp underscore Kelvin, it is equal to true underscore temp underscore C plus 273.15. So thermistor resistor model, thermistor resistance model. So this R underscore thermistor is equal to R naught into NP dot exp open bracket B multiplied by 1 by true underscore temp underscore K minus 1 by T naught. So this is the beta equation of an LTC thermistor. So how we will write it is written in code. Actual formula is R equal to R naught e power B open bracket 1 by T minus 1 by T naught. Now what is the meaning? When temperature increases, resistance decreases. When temperature decreases, resistance increases. So this line calculates thermistor resistance at each temperature. Then voltage divider output V underscore out is equal to VCC, that is supply voltage, multiplied by R thermistor divided by R underscore fixed plus R underscore thermistor. This uses the voltage divider formula. So in the code it is written, what is original formula? V out equal to Vs multiplied by R thermistor whole divided by R fixed plus R thermistor. Then what is the meaning? As resistance changes, output voltage changes. This voltage is what we measure using analog to digital converter. So temperature calculation from measured voltage. So T under for step 1. So find the resistance from measured voltage. So R underscore measured is equal to R underscore fixed into V out divided by VCC or Vs minus V out. So this rearranges the voltage divider formula to calculate the resistance. So step 2, it converts resistance back to temperature. Then T underscore measured is the Kelvin. In Kelvin, it is equal to 1 by T naught plus 1 by B multiplied by NP dot log R measured divided by R naught. So this is the inverse beta equation. So already we have written beta equation. So inverse of that equation is equal to T, that is starting T equal to 1 whole divided by 1 by T naught plus 1 by B ln R by R naught. So this gives temperature in Kelvin and convert to Celsius. T underscore measured underscore C. It is equal to T underscore measured underscore K minus 273.15. Then plot the results. So graph 1, it shows voltage versus time. It shows how output voltage changes with the temperature. And then graph 2, it shows the resistance versus time. So it shows thermistor resistance variation. And graph 3, true versus measured temperature. True versus measured temperature. And the solid line actual simulated temperature. Dashed line, it is the calculated temperature. Both should match closely. Then display final temperature. Print open bracket average measured body temperature 2F. So 2F means 2 space, and then C in degree C, that format NP dot mean T measured underscore C. It calculates the average measured temperature. It displays the result with 2 decimal places. So it will round off. And example output, average body temperature is 37.01 degrees C. And overall working principle, it simulates the body temperature and converts temperature into resistance. Then converts resistance to voltage. Then converts voltage to resistance. Then converts resistance to temperature. Then compare original and measured value. This mimics real thermistor based body temperature measurement system used in our biomedical instrumentation. So what is the value here? So we are getting this waveform. So in this case, we are using the sampling frequency of that means one sample per second, but the duration is 60 seconds. So this first one, it is simulating thermistor resistance variation with the temperature, and it is using the voltage divider circuit model, and then it converts measured voltage to resistance, and then once again the resistance value is converted into temperature. Then it is plotting voltage versus time, then resistance versus time, then temperature versus time. So what is the principle? This thermistor, because we are using the negative temperature coefficient, so that resistance and temperature both are inversely proportional. And then beta equation we are using, that is T equal to 1 by 1 whole divided by 1 by T naught plus 1 by B ln R by R naught. So what is the output we can expect? Normal body temperature varies from 36.5 degrees Celsius to 37.5 degrees Celsius. Small sinusoidal variation simulates physiological fluctuation. Then we are going to import the NP Python, that is used for mathematical calculation. So normally it will be used for logarithm, sinusoidal, exponential, and then arrays. And then we are going to import the library functions. Here no signal functions we are importing. So previous cases signal functions we will import, but here it is not required. So now the normal temperature thermistor specifications are taken into account. That means R naught equal to 10K. So 10,000 means 10K. Then T naught value, it is 25 plus 273.15. It is normal only. So beta value constant, but it may vary little bit depending upon the material used for manufacturing the thermistor. And then voltage supply voltage equal to 5 volt DC. Then R fixed resistor value is also equal to 10K. Then what we will do, we have to simulate the body temperature. So for that we will take sampling frequency equal to 100. Then time equal to line space, line space starting from 0 up to 10, and then fs into 10. So sampling frequency into 10, so that 10 into 10 100. So 100 samples per second we will have. So time axis is separated, partitioned from 0 to 10 second. So here to simulate body temperature, true temperature is equal to true underscore temperature underscore C is equal to 37 plus 0.2 NP sine 2 pi Ft. So normal body temperature 37 degrees Celsius. Small sinusoidal variation. So here only 2 will be given, but sinusoidal means positive peak, negative peak, so that plus 2 or minus 2. Then it simulates the natural physiological fluctuation. Then it will convert to Kelvin. So true temperature underscore that means the temperature in Kelvin, it is equal to from Celsius to 273.15. So it is getting added. Then calculate thermistor resistance using beta model. So R underscore thermistor is equal to, so that is the formula, R naught plus NP dot exponential, that means e power P into 1 by true underscore temp Kelvin minus 1 by T naught. Now, how it will be rewritten? R is equal to R naught of e power B open bracket 1 by T naught minus 1 by T minus 1 by T naught. Now, what is the meaning? If temperature increases, thermistor resistance will decrease. If temperature decreases, the resistance will increase. So this line calculates thermistor resistance at each temperature. That is what is given by the beta equation. Then voltage divider, because the resistance is variable, so depending upon the resistance value, voltage will appear across it. That is why V out equal to VCC, that is supply voltage multiplied by R thermistor divided by R fixed plus R thermistor. So the formula is rewritten as VO is equal to Vs and R thermistor by R fixed plus R thermistor. So next one, what is the meaning? As the resistance changes, output changes, output voltage changes. This voltage is what we are going to measure using analog to digital converter. Then temperature calculation from measured voltage. So in the step 1, we have to find resistance from measured voltage. So R measured equal to R underscore fixed multiplied by V underscore out divided by VCC or Vs minus V out. This rearranges the voltage divider formula to calculate the resistance. Second step, we have to convert the resistance back to temperature. So T underscore measured in Kelvin, it is equal to 1 by T naught plus 1 by B multiplied by log R measured by R naught, and this is the inverse of beta equation. Now T equal to, how we will write this expression? T is equal to 1 whole divided by 1 by T naught plus 1 by B ln R by R naught. So R means any value at that time instant, what is the value. So this gives temperature in Kelvin, and again we have to convert to Celsius. So T underscore measured underscore C, it is equal to T underscore measured underscore Kelvin. So whatever the value we have obtained in the previous equation, minus 273.173. Now we have to plot the result. So graph 1, we will get voltage versus time. It will show output voltage changes with temperature. In the step 2, we will get resistance versus time. So it shows the thermistor resistance variation. Then in the third graph, we will get true versus measured temperature. So solid line will show the actual simulated temperature. Then dashed line, it will show the calculated temperature. Both should match very closely. So in the display final temperature, we will print what is the average measured body temperature. It is to dot 2F. So C then degree C dot format NP dot mean T measured underscore C underscore C. It calculates the average measured temperature, and it displays the result with 2 decimal places. So beyond that it will round off. So in this example we are getting average measured body temperature is equal to 37.01 degree Celsius. So overall working principle, how it goes: first one, we will have to simulate the body temperature, then we have to convert the temperature into resistance. Then this resistance is once again converted into voltage. then that voltage will be converted into resistance. Then again the resistance is converted into temperature. Now compare original and measured values. So these mimic a real thermistor based body temperature measurement system used in the biomedical instrumentation. So first one we will get we will get the simulation of temperature measurement using an NTC thermistor. It applies Steinhardt equation and it plots the measured body temperature. And this code, what it does, it simulates the thermistor resistance variation with the temperature. It uses a voltage divider circuit model. Then it converts measured voltage into resistance, and once again it is converted into temperature, and then it plots voltage versus time, then resistance versus time, and then temperature versus time. So now the principle is negative temperature coefficient. So we know that temperature and resistance both are inversely proportional, and then it will use beta equation. Temperature is calculated by using beta equation. Temperature is calculated, and in general T is equal to 1 by 1 whole divided by 1 by T naught plus 1 by B ln R by R naught. So this measured R means whatever the value we have kept. So what we will get is the typical output normal body temperature, which is almost equal to 36.5 degrees C to 37.5 degrees C. Now small sinusoidal variation simulates physiological fluctuation, so that we are getting the final measurement. So here in this experiment we are using the thermistor value, which is equal to 10,000 here, so 10K. It is 10K. Then beta value normal, beta value almost constant 3,950. It may vary little bit depending on the nature of the material, and supply voltage is 5, and then R underscore fixed is equal to once again 10K. So these are the known parameters of the thermistor circuit. So the thermistor resistance at 25 degrees, so room temperature only we are going to take, it is 10 kilo ohm. So T naught equal to 25 plus 273.15. It converts 25 degrees C to Kelvin, which is equal to 20. We have to add 298.15. 298.15 Kelvin. Then temperature calculation must be done in Kelvin, so that the fixed resistor is used in the voltage divider circuit. Now we have to simulate the body temperature with Fs is equal to the sampling frequency of 1 sample per second, and then duration 10 seconds we are going to take for measurement. Then true temperature in degree Celsius is equal to 37 plus 0.2. So it is the amplitude, and then sine omega. So the angular frequency conversion 2 pi ft. So slight variation, and then true underscore temperature in Kelvin. It has to be converted into this the Celsius value. The temperature in C calculated from the previous expression has to be converted into Kelvin. That is why we are getting temperature in Kelvin, which is equal to true temperature underscore C plus 273.15. So we have to add this value. So finally we will get all temperature values in C. We will get temperature values in Kelvin. So next one, calculate thermistor resistance using beta model. So in this code, R underscore thermistor is equal to R naught into NP dot exponential. B into 1 by true underscore temperature underscore Kelvin minus 1 by T naught. So how we will write this expression? R thermistor equal to R naught into E power B into 1 whole divided by true temperature Kelvin minus 1 by T naught. So B into 1 by T minus 1 by T naught. So normally T in Kelvin that we know. So next one, voltage divider output. So if we use, if we keep the slide of the thermistor, that means rheostat from the zero value to extreme end, the resistance value will be increased, and depending on the value of the resistance, the voltage developed across that value from zero to the slide position, we have to measure the voltage. It will vary. That voltage is equivalent to taken as V out, output voltage. So this voltage output is measured for every thermistor resistance value. So and then we will get the we will convert into temperature using once again beta temperature, beta equation, that is inverse beta equation. So that we will get the average measured body temperature with the 2 decimal value. So with this we end this code and the explanation. Thank you.